Hello to anyone who's watching this. Um, I just got back from the dentist. That's kind of irrelevant to what I'm about to do, but at school, a few of my friends were kind of harassing me, um, in context of how I haven't really done like the more basic level of calculus, because that really teaching that stuff doesn't really interest me that much. But I feel like I might as well. So basically, calculus is looking at the rates of change, and rates of change can generally be found in things like derivatives. So as you can see, right, if you have a function, let's say it's just 2x, right? So 2x would normally just look like that. So it hits 1, 2, and then it hits 2, 4, and then it hits 3, 6, etc. Now, a derivative is essentially looking at what is the rate of change at an infinitesimal point, very small point, the rate of change of that. So, say your position is 2x, your speed is the first derivative, so f prime x. The acceleration, hold on, I gotta increase this so it actually has acceleration. So, the acceleration is f prime prime x, so the speed of the speed, so how fast the speed increases, and that's generally, the way I understand derivatives to be. And this is a symmetric definition of derivatives, but generally they're more considered to be, like the true non-computer definition would be, just going forward. And also this would really, for an actual derivative, be like 1 over infinity. So, what else should I go over? Maybe I could go over like some like the limit definition of a few things. So maybe like the limit definition of e. So e. Okay. So e is that. It's 2.71828182846, etc. So the method to find how e was actually found was it was using this formula. So 1 plus 1 over x to the x. So as you can see, as this increases, it starts really leveling out pretty quickly. And as you can see, it's never going to get over e. So as you can see, so let's just check this. Let's call this fx. And then say f 100,000. It's pretty close, overall, all things considered. Let's say a million. Let's say 10 million, 100 million, a billion, 10 billion, 100 billion, and, a trillion, 10 trillion, 100 trillion, quadrillion, 10 quadrillion. Whoa. Well, that's because the Desmos can't really handle numbers that big, but that's not really the point. It's great, because it's the natural, like, it's like saying 1.01 to the, what would that be? Whatever, let's call it like 100 or whatever. But the point is, shrink the difference between 1 and a point super small, but then raise it to a basically infinity. So it'd be like 1 plus 1 over infinity to the infinity. See? Oh, and Desmos is going to say that's undefined, but that's e. So that's the limit definition of e. It's used in things like log natural, which is like this. Log natural e is just going to be 1. Log natural 4 is going to be that, etc. It's also used in Euler's identity for rotations. So rotations would be, let's go to this one, like this. Yeah, I was kind of messing around in this, but this is basically just looking at points, and then there's a point rotating another point, which is then going around with another point. So I think it was this was pretty interesting to make, but as you can see, it's just based on this here. And I think I should go to a better one here. There's a better one. So, yes, okay. So, e to the I... Okay, can we stop it? I'm going to reset. Because that's going to be laggy. E to the I pi is just... Oh, yeah, I need to turn on complex mode. Whoops. So, e to the I pi is -1, so e to the I pi is -1, so e to the I pi plus 1 equals 0. That is Euler's identity, and it's basically looking at the rotation of a point. So, e to the I, like angle, where angle equals true angle over 180 times pi, to convert degrees into steradians, which are used in complex numbers like this. So, let's say A is like 360 degrees, it'll circle back to 1. If it's 270 degrees, it'll be down here. And then at 180 degrees, it'll be right here. Or like, yeah, there, because it's 1. And then at 90 degrees, it'll be there. So that's Euler's identity, and it's used for complex numbers. It's essentially saying I have this in a graph as well for this. So as you can see, this is the formula to find... is that right? Whoa, I don't know what I was doing here. I don't really come into these with like scripts or anything, so I just... Yeah, and this as well, right? I'll pause this. So this point is circling through the path of this point, so it's essentially rotating around like that. And the formula for the rotation is this. So the length around an axis times the horizontal component in the unit circle. So there's a unit circle where everything's 1. This is cos, this is sine, to reach any point along the edge, right? And that is essentially what sine and cos is. And in this case, we're taking the angle inputted into cos, and that's gonna be some value -1 to 1, and then we're gonna multiply that by py to represent the length. And then it's gonna be the same here for the px sine a. Also, this is the y coordinate. So just know that is the y coordinate. This is the x coordinate. So if you ever want to do a rotation, that is the way that you could do that. But also, the complex version works the same as well. So e to the pi I. Why doesn't it automatically turn on complex mode? Okay, so e to the pi I is Euler's identity. What else could I talk about? I think that's good for today. I think that's pretty okay. Yeah, this doesn't really have like a specific thing I'm going for. It's just putting a bunch of different topics into this, and then maybe someone will ask more about one or something. So, yeah. And also, I didn't post yesterday, so I felt kind of obligated to post today. So, thank you for watching if you did. Bye. That was awkward.